Hi guys. For our compiler project, we need more flexible data structures. So far we just have arrays with a fixed number of elements or linked lists, but also just with a fixed number of list nodes. And this is certainly not flexible. What we need is data structures that can grow. And for that we need dynamic memory management. And the C standard library provides us functions for doing that. And this video is mainly about that, also about related topics like pointer arithmetic. I will first just introduce you two functions from the standard library that can be used for this dynamic memory management. With function malloc, you can reserve a new block in memory with a given size in bytes. And if this function is successful in reserving such a block for you, if it finds a block that wasn't used so far for something else, then it will return its address. And this is in C just a void pointer. So it basically means you have a pointer that points to the first memory cell in this block, but it's not specified, at least so far, what is at the end of this pointer. You can later typecast it into another pointer type where this is actually then specified. But that's another story that comes later. Reserving a new block, as I said, means that this block shouldn't be already in use for something else. So it should not be part of the text, data, or BSS segment, and it also should not be part of the stack. Now, the stack is a growing structure. That means, in our case, it's growing downwards. And this is typically like that on all platforms. So in order to make it possible that in most cases, you always get something which never will be part of the stack. We simply assume that this is far away from the stack. It will be, in our case, when we implement this on the ULM, between the BSS segment and the stack. It starts right after the BSS segment and it will grow upwards. So it will also be possible to increase the size of this region where we get this new dynamically allocated memory. But sooner or later, if we reserve lots and lots of such blocks, we also will run out of memory, because reserving something means that a subsequent call of malloc should give you back a block that is disjoint from all previously reserved blocks. So certainly it also should be possible to give back a block to make it available for subsequent mallocs again. And for that, you can use this function free. Now, of course, you will see use cases, how to use this for creating lists that dynamically can grow, for example. But it's also interesting to understand how malloc and free could be implemented. Of course, we first should know how malloc and free can be used before we try to implement it by ourselves in a simple way. And most of all, what kind of pitfalls we have to avoid. In the demo, I will first show you examples where this malloc always succeeds, so we will not get back a null pointer. And first I will just allocate a block with 123 bytes. So I will store this address in a pointer p, and then I will allocate another block with 100 bytes, and I will store the address in q. Then I will also print out these addresses, show you that the distance between these addresses is sufficiently large so that we actually see these are not overlapping blocks. Then I will release memory. I will release the block to which p points. And this will not change the value of p because we have call by value. That means p now points to this now released block. And that means a subsequent call of malloc could use these memory cells that are now available again. Or it could give us back a memory block which is not overlapping with this released memory block. And these are two scenarios that you always have to keep in mind. If you have something like here, where you have a pointer which is not the null pointer, but also not pointing to reserved memory. So the first case will be that this third malloc gives us back the address of a block that is not overlapping with any of these previous blocks. And the other scenario will be that this block actually is overlapping. And you will see that this often results in programs that sometimes do what they should do or what you want or expect them to do. And sometimes they are doing this not. And sometimes people think about this Like on sunny days, the program works, and on rainy days, it's crashing. You see, compared to the example on the slide, I added here a few printfs so that I see after each malloc, for example, and after free, what are the values of these pointers. And now let's first run this program to show you what we get currently. So this is the address of this block after malloc 123 in hexadecimal. This is the address of this block after malloc 100. You see that the distance between these two addresses is certainly larger than just a few hundred bytes. So we do have disjoint blocks here. Then I release memory, and the value of p, of course, has not changed because of this call by value. And then I allocate another block, and the address of this new block is also far away from this previously allocated blocks. And although I have released this block to which p points, I do get a new block. Now let's change this program so that it's also printing in decimal the distance between these addresses so that we better see whether we have disjoint blocks or not. So I print the absolute value of, for example, p minus q, and then I will change it so that I also can see the distance between p and foo and q and foo. The type for the difference between two pointers is pointer diff, and for printing this in decimal, I can use this format TD. And it's platform independent. So here, if p is smaller than q, then I want to print here q minus p, and otherwise p minus q. Now I just change it so that I also can print the difference between the distance between p and foo. And actually smarter to do it like that. And also the distance from q to foo. And then you will see, by the way, if I run this program again, you will get different addresses for p and q. And this actually changes in general each time you run a program. There is no guarantee that you get the next time for a block the same address. So before I compile it, I already can show it you here. So new addresses, but still in this case, somehow it's always the same, that the distance between p, q, and foo is always more than just a few hundred bytes. Okay, but now let's run this new version, which is actually showing us clearer the distance between these addresses. So yeah, certainly more than just a few hundred bytes. And now I will do a minor modification, which will cause by my implementation of malloc on my computer together with GCC, that after releasing this block to which p points and allocating another block where I use the same size of the block that was allocated above here, you will see that this implementation of malloc will give me, in this case for foo, the same address that I got up here. And then you see here the distance between p and foo is 0. So now they both point to the same address. You also, of course, see this here. Now, why is this a very dangerous situation? Let's assume that down here you actually make use of these 3 pointers. So use p, q, and foo. And let's assume that your program works if you have 3 disjoint blocks in memory. This is certainly the case if you would not have called here free p. And if you do not have disjoint blocks, it somehow will either crash or do something unexpected. And then later in the development cycle, you somehow come up with the idea that you actually could release the memory because you forget that later you actually require this memory, then you have the situation that sometimes your program works as before because you still have pointers to disjoint blocks, and sometimes this is not the case. And it depends on the implementation of malloc and what parameters you used for malloc, what block sizes you use. And having a program that just works on a good day and doesn't work on a bad day is the worst. What you want is well-defined behavior. Either it works always or never. And to get closer to this, you can use in connection with pointers the convention that a pointer should either be the null pointer, which means it's invalid. You should not use this pointer for accessing data, or it's pointing to allocated data. That means it's valid. And that means after free, where you still could use this pointer later, you also should set it to the null pointer explicitly by yourself. And then you will see later if you have a virtual memory that supports certain memory pages to be invalidated, which is currently not the case on Ulm, you will always get a crash if you use a dereferenced null pointer. This is not implemented in C. It's implemented basically in the hardware. If a virtual memory page with address 0 is accessed in a fetch or store operation, you can implement a virtual memory so that it's always giving you a segmentation fault, which is not nice to have a segmentation fault, but it's better to have that compared to this undefined behavior. Okay, but let's continue here with also showing you that you will get a null pointer if you run out of memory, for example. So I will simply use here a loop without a for loop without condition. So I have here a loop that will never terminate. And then I want to here allocate memory and allocate and never release it. And I will use variable for the block size, which initially will be 1. So I can do that actually here. And the condition stays empty. And then I just double the block size each time. And then I print the value of p. Maybe I also print what I allocated, what block size. And then I also have to include here standard def for size t. And then you see, sooner or later you get back 0. So maybe we should make this the condition to exit the loop. And of course, in this case, I simply could add here a break. And I could check here whether p is the 0 pointer, but the typical convention is to just use here this logical not. If p is not valid, then break the loop. Let me show you how you easily can come up with your own implementation of malloc and free. And in the assembler programming part of this lecture, this is actually how you will implement these two functions so that we also have some dynamic memory management in the assembler programming part. Under Unix, there is a so-called system call for accessing the breakpointer of a program. The breakpointer of a program is an address right after the global data, so an address after the data and BSI segment. And with that, you can implement malloc as follows. You will, in the end, return the current value of the breakpointer. That means you first make a copy of its value. Then you increment this original value by the number of bytes that you want to reserve. And then you return the copy that you made before. And that means if you would call this implementation of malloc with parameter 123, it will return the current value of the breakpointer, but afterwards the breakpointer would be incremented by 123. And if you then would call malloc with parameter 100, you would return the current value of the breakpointer, but afterwards it's incremented by 100. And by that you make sure that no block would be overlapping with a previously reserved block. So this is the key requirement for having a standard conform implementation of malloc, that you actually can reserve blocks of bytes. And the only thing that you also have to consider is that it's required that these pointers are aligned. And the pointers have to be always aligned to 8. So the addresses have to be a multiple of 8. That means you have to make sure that the first time you access the breakpointer, you round it up to a multiple of 8. And if you actually reserve a certain number of bytes, you round up this number of bytes to the next multiple of 8. But that's not so difficult. Now, how do you implement free? Well, the simplest way to do that is simply do nothing. So that means, of course, you are wasting memory a lot. Yeah? You soon run out of memory because you never can give it back. But it's still conforming to the key requirement that you have these reserved blocks and that they're aligned to 8. Of course, we will later come up with a better implementation of malloc and free, where it's also possible to give back memory so that subsequent calls of malloc actually can reuse this memory. This will require some data structures for managing available memory and already used memory. And we will have a very simple implementation for that, but you will see the principles and how in general this malloc free implementations are implemented or could be implemented, and most of all, why they always come in pairs. In C++, for example, you have this new operator for allocating memory, and it comes together with the delete operator. And also if you use certain libraries like the fastest Fourier transform in the Western, it also comes with its own malloc implementation, but also with its own free implementation. And in our implementation, I can basically tell you more the details. It will be as follows. If you call malloc with a certain parameter for how many bytes you want to reserve, you will give back a pointer to this reserved block, if such a block is found. Otherwise, of course, a null pointer. But in front of this pointer, we will store some additional information. This additional information will be required for our data structure. And in our case, it will be, for example, the size of this block and the next pointer, because we will manage this in a list. And from that, it's kind of clear how free can know how many bytes should be released, because our free implementation knows where malloc is storing this information about the block size. And so obviously our free implementation has to match our malloc implementation. And it also will give you an idea why misusing malloc and free might completely destroy these data structures and will have some completely unexpected behavior of your program. For example, if you call free more than once, you could destroy something like a next pointer by that. And that means a subsequent call of malloc, which can come somewhere else in your program, in a completely different place, will cause a crash or some undefined behavior. And it's very hard to track that down to the origin of the problem, that originally you just called free just more than once. The same can happen if you call free on a pointer that was never returned by malloc. So there are certain things that if you do that, you can completely have undefined behavior. And so we need some rules how to use malloc and free properly to avoid this common mistakes. So this is just another pitfall that we have to avoid. Making proper use of malloc and free certainly requires some discipline and good design patterns to avoid all these pitfalls. But with that, with discipline and design patterns, you will see that you can avoid these common pitfalls. The next thing that we have to talk about, and where we also will have certain pitfalls that can be avoided with certain patterns, is using the data that we allocated. We cannot dereference a void pointer, because by definition, a void pointer is a pointer to some data where it's unspecified what kind of data we have. So you first have to cast this pointer into some proper type. And here in this example, I already allocated memory for 4 integers. And of course, I want to use it as an array of 4 integers. And in order to do that, I somehow have to dereference this pointer so that I can write something to this memory block. And in order to do that, I first have to convert this result from malloc, this void pointer, into an integer pointer in this case. And I can do it like that. And actually, I can write this down a bit simpler because it's commonly required to cast a void pointer into an integer pointer or some other pointer type. And this will be implicitly done if I write it like that. So I do not have to explicitly state that. The next thing, and this is about pitfalls to avoid, you often will change after a first design the type of the elements in such an array. For example, let's say I now come up with the idea that I actually would like to have 4 doubles in this array. And then I might change it like that, and then I have a problem, because what I have reserved is 4 times the size of an integer. And the double has more bytes typically compared to an integer. So I also should have changed the size of int to size of double. And to avoid that, it's a simple trick. Simply use size of the dereference pointer type. Because when the C compiler passes this line, at the equal sign, basically it's already clear that this is a pointer to some type. And that means you already have this entry in the symbol table, and that means you can use already the dereference pointer type for this argument of size of. And now if I would change it back to pointer to integers, I do not have to change more than just this type at the beginning of this line. So this is kind of nice. Now let's write something to this array. I first want to write something to this first element in this array. I want to store there a 42, of course. So I simply dereference this pointer and then write to this dereference pointer. So that's it. Now I have stored my 42 in this array. Then I want to write something like, for example, 13 to the next element in this array. For that, I have to increment the pointer by the number of bytes that are required to store an integer. That's at least how we would do it in assembly. So I would have to know what is the size of an integer. Of course, I get that with size of int. But actually, this kind of bookkeeping is done by the C compiler. The C compiler now knows, in this case, this is a pointer to an integer. And if you increment it just by 1, it increments it by the size of integer. If I would change it back to a pointer to doubles, it would increment it by the size of double. So this is this pointer arithmetic. If you have an expression where you have a pointer plus an integer, you always increment it by the number of bytes of this element type times the integer that you add. And now, of course, we could access this next element by just incrementing the pointer by 1, dereferencing it, and then store the 13. But actually there is a way to express this even nicer with this index operator, because there is this convention that if you have an index operator, that means you have 2 operands, in this case x and y. Y is the index. Then it's equivalent to just taking the sum of x and y, which is a pointer, because a pointer plus an integer is again a pointer, and this will be automatically dereferenced. So I can simply rewrite this whole thing like that, because the elements just can be accessed with array index operator index into that. And that's it. On the website, you will find this example for a vector class implementation in C. And it's supposed to show you that certain design patterns and following certain rules can help you to circumvent some of these pitfalls that you saw before. How can you use this vector class? Well, you see that we have here a struct vector declaration, a struct with 2 members. This member dim, of course, is for the dimension of the vector, and this pointer data points to the first element of the vector, and all elements of this vector have type double. You also see that these members have this const qualifier, such that once you have a variable of this struct vector type, you cannot change afterwards the value of dim, and you cannot redirect this pointer data. That means data will always point to the same memory location. So how do you initialize instance of this struct? Well, you do not do this by yourself. You simply call this function for constructing an initialized instance, and this function receives a parameter for the dimension. Internally, of course, it will call malloc. It will check whether malloc returns a null pointer or not. If it returns a null pointer, it will do some error handling. It simply will terminate the program with an error message, and otherwise you get an initialized instance of struct vector. And that means this instance has a pointer that actually points to an array with dim doubles. And of course, if you leave the scope where this variable of type struct vector was defined, you should release the memory. And you should do this by calling this function, which expects a pointer to this vector. And internally, of course, it will simply call free. If you want to change an element in this vector, but also want to be sure that the index to a certain element is actually valid, whether you're inside of the vector dimension, then you can use this function. It first expects a pointer to a vector and a second parameter, an index. Then it first will check whether the index is valid. If this is not the case, it will terminate with an error message, and otherwise it gives you back a pointer to the element that you want to have. And if you just want to have read access, but also this index check, basically you have the same function as before. It just returns not a pointer, but the value of an element. On the website, you will also find examples how to use this and, for example, initialize a vector with certain elements and print this vector. And you will also see that this is basically equivalent to the following C++ implementation, where just the compiler, the C++ compiler, automatically, for example, calls this construct function where it is needed when you instantiate this variable of type vector, and it automatically will call the destructor before you leave the scope. So you, for example, cannot forget to destruct a vector before a return statement. So this is kind of convenient for using C++. But most of all, it also shows you that certain C++ code always can be considered as a special case of C code, where the C++ compiler just generates C code at places where you could forget it. So this design pattern for this vector class in C helps you to prevent certain problems, but still requires some discipline. And the C++ compiler goes just one step further. It helps you to avoid even more problems, but it's still equivalent to something that you could do in C. With malloc, you do not get a zero initialized block of memory, if you get a block of memory at all and not a null pointer. If this block that is returned by malloc was already in use, you will find eventually leftovers, similar to the stack. If you want to have a zero initialized memory, then you have to use calloc. It also will return a null pointer if none block of this size is available, but otherwise you can be sure that it's zero initialized. If you want to change the size of a previously allocated block, you can try to do that with realloc. If possible, it will simply increase the block size. Otherwise, it will try to find a new block with the desired size, the desired new size, and will copy the data to there. And of course, if this also doesn't work, if there is not enough memory available, it will also return a null pointer. You will find examples for both of these two functions on the website, of course. For the video, that's it. Bye.